Welcome everyone. My name is Andrew Ashton. I am with Centria. More importantly, I'm with Reina. I serve on the board of directors and the executive committee of Reina. And today we have the eighth presentation in our deep dive into Rainscreen series, partnered with RDH. Very excited to present the topic pressure equalization. Um, this is definitely something that John and I have gotten into a handful of times, and it's always a pleasure to go down this. So I'm looking forward to today's presentation. If you want to flip that slide, John, we'll talk a little bit about Reina.
Yeah.
Reina, our mission and vision. Our mission is to work together with our membership, industry, and trade to be the recognized authority on Rainscreen wall assemblies in North America. And our vision is to be the recognized Rainscreen authority supporting performance-driven Rainscreen assemblies that contribute to more durable, resilient, healthy, and energy efficient and safe buildings. The way that we achieve that is through a combination of things, but primarily our values drive that, which includes the integration of expertise, such as the folks on this call, not myself, but John Straub with RDH, sustainable, long-lasting building envelope enclosures, building science-based performance criteria, and design aesthetics. And as a member of Reina, there are some pretty neat benefits that bring to the member companies, which is the opportunity to influence the industry, such as participating in committees, setting standards, influencing change to building codes. And one great example of those top three things is we developed a definition for Rainscreen that is now currently residing in the IBC. So it was a combination of the definitions committee working along the codes committee to really influence the industry there. Also, as a membership parting benefit, you're able to stay informed of what's going on in the industry. And part of that includes getting caught up on the Rainscreen series that we have today. If you take a look, we have a link here. There are 8 parts to this series. Again, today is the 8th and final. Currently 5 are live on the Reina website. We plan to have 6 and 7 up shortly, along with 8 following the conclusion of today's presentation. And with that, I'll pass it over to the Principal and Senior Building Science Specialist for RDH, Dr. John Straub.
Hello. All right. Thank you, Andrew. Yeah, pressure equalization. It is true that there's not a lot of people who care enough about this to get into conversations with it. And Andrew is one of those special ones who I actually really appreciate that because, you know, you can get into some of the stuff and ask questions. And so today I want to, it can only be an introduction. Even though this is our final session, we left it to the end quite importantly and deliberately because it isn't the be all and end all of Rainscreens, but it is something that's closely related to Rainscreens and that serious designers are often going to be asking, okay, I understand the Rainscreen stuff, but I want to do a pressure equalized Rainscreen, which is the next sort of step towards nirvana. And so pressure equalization was also one of the core topics in my graduate work, because at the time I was doing this graduate studies, pressure equalization in the field was an area of real interest. And that got me started down this path. And frankly, it's interesting is that, you know, 25 or more years later, we're still talking about pressure equalization and still doing research to refine some of the nuances. And I'll tell you kind of the things that are left over. Now, I'm always going to start this kind of a seminar with what is a Rainscreen. And as Andrew said, one of the things that we have now from Reina is a definition that is deliberately broad. Notice it says an assembly applied to an exterior wall, which consists of outer layer, inner layer, a cavity between them, sufficient for the passive removal of liquid water and water vapor. And it's quite helpful, believe it or not, to have such a pedantic definition. Now, typically, this is what people would look at as a wall system, as a Rainscreen wall would have that cladding as the outer layer. The airspace or gap or cavity behind the cladding. Then there is a water resistive barrier, which would be the inner layer in this definition, but something that isn't always there, but in practice is almost always, is that you need flashings. You certainly need drainage openings. And this is all supported by something, a backup wall structure, whether that's cast in place concrete or wood studs or anything in between. So those are the basic minimum functional requirements. But in a modern day, we also have insulation, particularly an increasing amount of insulation that's located outside of the structure to minimize thermal bridging. We also have to worry about things like cladding attachment systems. This is a huge deal in terms of doing rain screens, a practical issue. And we also have an air barrier system here. For a rain screen as written, you don't need an air barrier, but we know for a modern wall, we need an air barrier and we need insulation. So that's why we're showing this as a more complete description. Now, we have made this 8 sessions because we thought through the definition and thought, what pieces could we break down? So first, number one, Finch did an introduction. What are rain screens? Why do we use them? What are they good for? Then I presented some of the history and its development, and it's actually quite significant how Europe, Japan, and North America, New Zealand, how we went down different paths, and there remains confusion between these different parts of the world because of that different history and the different words and definitions. But we started getting into the cavity, the parts of the rain screen wall, and focused on liquid water removal. So that means drainage, a whole 1 hour session on that. Then we looked at the passive removal of water vapor, where we can dry things out, make sure that condensation can be forestalled, and we do that by ventilation, which also needs a cavity. So that was a whole session number 4. Then we talked about the last line of defense in the Canadian Building Code, which is the water resistive barrier in the American building codes. So that was session number 5, all of the options and details. Number 6 was cladding attachments, practically needed, but not here in this definition. Number 7 was the cladding itself, which is the first line of defense in the Canadian Building Code. And the thing that actually is usually the most expensive part of the entire enclosure. Even though people spend a lot of time trying to save money on insulation and WRBs, by far the most expensive thing is the cladding. But the cladding is what people see. It's what has to survive the elements for unprotected for a long period of time. And so that's why there's a whole hour on that. Now, today, also not listed on this, we're going to talk about pressure equalization. So pressure equalization is not a fundamental requirement, meaning you don't have to have pressure equalization for a modern rain screen wall assembly to work. Historically, we added pressure equalization as a feature or a component to essentially already functional rain screen systems that already had a cladding, a gap, a water resistant barrier, flashings, and those are the walls that we added pressure equalization to. It's important to recognize that distinction because sometimes the conversation about what does it take to make pressure equalization doesn't remind you that you really need a water resistant barrier and flashings. And that I'm reminding you of that, and you need to remind yourself of that. So today I'm going to go through what is pressure equalization, how does it work, why would we use it, and then I'm going to dive into the nature of wind pressures, which is going to lead us into some interesting conclusions and observations. So let's talk about pressure equalized wall systems. The intention behind pressure equalization, whether it applies to a joint between precast concrete panels or a window to sash joint or a whole wall cladding, is it's encouraging the equalization of the exterior wind pressure with the air pressure behind the cladding. The image on the right-hand side is from one of the first guides that was presented in 1971 by AMA. And this was focused on curtain wall design. And it was basically the idea was if you just had a single layer that was your cladding and was your water control, wind pressure would blow air up and over any cracks, joints, and openings. And so the concept shown in drawing number C was to acknowledge that that cladding was not perfectly watertight. And therefore, water was going to be blown through a hole. So they recommended complex joint details to resist the direct flow of water droplets by having labyrinths and gaps and nice overlaps, but also to ensure that it was an airtight wall so that the wind would not blow through the unintentional openings, dragging water with it. By allowing the wind pressure on the outside to freely enter behind the cladding, the concept was we could reduce or eliminate water that was driven across both intentional and accidental openings in the cladding. This freed up us to use all kinds of cladding systems, not having to focus on joints, and helped reduce water penetration problems that had been experienced in many different wall systems. This came about after literally 30 years of researchers studying rain penetration and talking about it, but it took a long time, as it usually does, to get into the mindset of the building industry. This is a recreation of two drawings, the 1971 guide on Rainscreen, and also the 1963 guide from which it references material. This shows us that if you're interested in managing rainwater penetration, there are 6 mechanisms that could drive water. And I think everyone understands gravity, right? You shouldn't tuck your pants into your boots, as I described. That actually remains, in my professional experience, the most common cause of water leakage in buildings. It is unintended inward sloping or cracks and openings that slope inward that bring water in. If you have a big enough opening, water droplets flying through the air can just pass right through the hole and into the building. Last session, we talked about open jointed claddings. A unbaffled open jointed cladding allows a lot of water to penetrate by mechanism B, kinetic energy. Surface tension allows water to cling to surfaces, and that water running under the force of gravity can then, if the surface bends inward, drive water into your assembly. Again, pretty easy to design that problem out, but occurs accidentally in many practical situations. Capillarity is actually not a force that will drive water through a cladding, but it is a force that drives water into a cladding. The same force that drags water into the small gaps that are indicated will hold the water. It won't allow the water to across the cladding, across a cavity, or anything else. It'll only suck the water into the concrete or brick or crack in the window. So E and F mechanisms are the ones that pressure equalization was intended to solve. Air currents, where the air pressure difference drives airflow into the building, can be quite powerful at dragging water into undesirable locations, like your living room. And that type of air current is easy to solve. I put air quotes around easy, by having an effective air barrier. When pressure equalization as a concept was developed, air barriers were not commonly installed. They were not deliberately named. And so no one ever made the connection between having a good airtight layer on the inside of the building and water penetration. So this is a pretty big deal. Of course, in the modern world, most of us know we want to have a good air barrier for a whole bunch of reasons. Now, pressure difference, number F, is directly what pressure equalization today will still help us solve. And that is water over a moderate size gap, not so small that capillary forces will hold the water, and not so large that water just flows away. Over a certain size of gap, a film of water can form, and when there is a higher pressure outdoors than behind the cladding, water could be pushed into the wall cavity or even further, depending on how the wall is designed. So again, the pressure equalization as a concept was being promoted, although not widely used, by the 1960s. These are some old drawings. That's the reason that their clarity is so poor. And it was defining the cladding as a rain screen was just to reinforce the fact that the cladding wasn't stopping water. So a rain screen cladding is really a cladding that leaks rainwater. That's not hard to do. The hard part is the rest of that rain screen. Now, you can see here, by today's definitions, none of these walls would be seen as actually reasonable as a choice. So, for example, in the brick veneer over the wood framing on the far right, it shows the sheathing paper as an air barrier, not as a water control layer, not a water resistive barrier. And you'll notice the flashing does not tuck behind the sheathing paper. And this is because they hadn't yet recognized how important drainage was, and hence how important weep holes and flashings were. And so they were really pushing the idea that these weep holes were ventilating openings, and that the sheathing paper, WRB, was an air barrier, and that was the way to get good rainwater control. So this is another image from another very important document, Garden 63, Svensson 67, very important seminal documents that started us down this road. But we didn't really have an air barrier as a language or a water resistive barrier. We didn't really have that clearly stated, as I would say we have in the last 20 years. So this slide is just reminding you of what I said. Air barriers were not standard. Water resistive barriers were not a thing. But today, when we interpret how we should move forward, we have to recognize that rain screen walls, what we talked about in the previous 7 sessions, absolutely have a water resistive barrier that is water resistive. It's integrated properly with flashings, which connects to weep holes to get the water to the outside. That's rain screens. Also, modern walls have great air barriers. We're increasingly testing our buildings to make sure that our air barriers are good. So those things are now inherently part of accepted minimum practice, not even best practice. So pressure equalization adds a component to this. It says we want to manage air pressures across the rain screen, across the cladding, to reduce the amount of water that will pass because of air pressure differences. Remember, all the water leakage that previously occurs with no air pressure differences still occurs. Pressure equalization deals with that wind pressure difference as a force. So the 5 components that were identified, this idea from the 90s, that you needed was a cladding, an air chamber. It's no longer a gap, and that's because it has these compartment separators, which we'll come to at the end of this session, about limiting the size spatially of the air gap. There's an air barrier and there's a vent. I intentionally didn't show you a water barrier, flashings, integrated, because that's not what pressure equalization is about. That's what rain screens are about. But a pressure equalized rain screen pushes all these things together to get the best in performance. So the theory here is that we're looking at the bottom of a wall. The blue line is your air barrier. The wind pressure is rising or falling or blowing hard on the left-hand side. And that's the green box to say that when the wind blows on the outside, it enters via the vents into this chamber. And so now the pressure on the inside is the same as the outside. Ergo, no pressure across the cladding. And that means that if there was a crack or opening across the cladding that would have allowed air pressure differences to push water in, then it would no longer work. So it would not drive water anymore. If you have a downward sloping crack, however, gravity will still drive the water in. So, this is all about solving this air pressure difference. So let's start with thinking about pressure equalization in a static sense, and then we'll talk about dynamic, and then I'll talk about spatial dynamics. So static pressure equalization is thinking about the wind as a constant, steady pressure. And by steady, I mean steady over 10 or 30 seconds or something. So you apply a pressure. Let's say it's 20-mile-per-hour wind is hitting the face of your cladding. That turns into a pressure of some 100 and some pascals, or I don't know, quarter-inch water column, something like this. That uniform pressure will easily, the air will flow into the chamber and absolutely get close to equalizing across the cladding. The reason I mention it is in the way I have is that that's not how the wind is in real life, but it is how we do most water penetration tests. A uniform, steady pressure, and that means that all you need is a good air barrier and even a small vent, and you will get equalization. Because within 10, 20 seconds, even through a small vent, air will flow from outdoors into the chamber, equalizing the pressure across the cladding. And so if you were to measure the pressure at many spots across your wall system, it would follow the green dashed line on the right-hand side, showing that there's the same pressure on the outside as in the chamber, and it only drops across the air barrier. And that's how we do most on-site tests. This has nothing to do with reality. I'm just telling you this is what the tests are. And that's an important takeaway. Now, let's say I had a wall from 1980 and it was quite air leaky. I'm showing that as a gap in the green line. And the red arrows show the airflow through the vent and into the chamber, along the chamber until it finds the air leaks that are in my air barrier. Under this scenario, where I've said the air barrier leakage and the vent leakage are about the same, an arbitrary choice, then I would say I would know we can prove and measure that half of the air pressure difference would be across the cladding and half would be across the air barrier. And because of that, a significant amount of air would flow through the vent and drag droplets with it. And a significant amount of air pressure would act on the cladding and drag any water that was present through cracks and openings. And so this would be 50% pressure equalized, the image on the left. Now, most of the time, we either have more airtight walls than I've just shown, or we have much larger vent areas. In the example on the right, I'm showing an example where the vent area is 5 times that of the air barrier. In that situation, about 96%, that's an error, 96% of the pressure across the whole assembly would be experienced across the air barrier. And that means only 4% would be across the cladding. So with reasonable amounts of venting and a reasonably airtight air barrier, under steady pressure conditions, you can get very close to perfect equalization. And that's what the first 30 years of experience and measurements was focused on. Now, how much vent area does that mean? If I use the Canadian and American standards for wall air tightness, you end up with something like 0.1% of wall area as vent area. So I would, often like to see it higher than that, but that's a reasonable starting point if you want a number. about how big the vent area needs to be. And
John,
there's a,
real quick,
yeah,
does
go
that
ahead.
test method allow for some conservative assumptions? Is that why it's assuming to be continuous and evenly applied? That's a question
No,
from Paul Reynolds.
oh no, it's not conservative at all. It's the opposite of conservative. Because it actually, those steady uniform pressures are easy to pressure equalize. So the moment you have even a modest attempt at venting and air tightness, all systems are pressure equalized. And that's very common, like window tests. We do 15-minute window tests. As long as you have a reasonable attempt at venting the frame, they're all pressure equalized. But that doesn't mean that they all work that well, as we'll find out in the field. So, however, I want to point out that I find it surprising as I look at modern systems that this is a cladding system, an ACM cladding system, and the vent openings for these panels are 5/8 of an inch by 1/8 of an inch. This is barely enough to let water out. And the area is probably, well less than 1/10 of what's needed to get close to an air pressure equalization at a reasonable level. So this is a bit surprising, but it's not uncommon. And so larger openings, more often openings, or even slots are usually easy steps forward to achieve this steady pressure equalization. So these are highly vented systems. We talked about these in the last session. If you have this many vents in your cladding, you can be pretty darn sure that the air pressure behind the cladding is equal to the air pressure on the outside of the cladding. However, you can also be pretty darn sure that lots of rainwater will directly pass through the cladding. And so there's always a little bit of that trade-off. The historic pressure equalization rain screens were all about protected vent openings. But that doesn't mean that these systems I'm showing on the screen can't be quite successful. It just means that they are not successful because they're pressure equalized. I mean, they're pressure equalized for much of the time, and yet lots and lots of water passes through. So you have to figure out how to manage that high level of water passing through. So I want the key takeaway from this chunk to be that walls with good air barriers are almost all pressure equalized to static pressures with even modest vent areas. So, reasonable vent areas, good air barriers, and when you do a steady test as per most standards, it's going to work as a pressure equalization. So let's get a little deeper into this. First of all, the concept that we're pressure equalizing because we're wanting to manage water penetration through the cladding, you can't forget that water penetration through the cladding is likely to occur anyways. Even at zero air pressure difference across the cladding, there are those other mechanisms, surface tension and gravity being key, that can drag water in. I've shown a crack in this cladding that happens to angle downward, which means that it doesn't matter how pressure equalized you are, water will leak in. And that's why Rainscreen systems say, yes, and I have a cavity, I have a water resistive barrier integrated with flashings and a weep hole, and that leak is not a problem. So that's how we would normally approach a Rainscreen wall. Now, another thing to keep in mind is that leaks that occur not in the cladding itself, but at penetrations like canopy attachments, window and door penetrations, balcony penetrations, routinely have water ending up on the water resistive barrier. Now, you might think that's not a problem. I agree with you that water on a water resistive barrier isn't a problem. However, if I have pressure equalized systems, as I show on the right-hand side, now 100% of the wind pressure that's acting across the enclosure is acting on the water resistive barrier, which now has water on it. And so you actually are putting there's a higher performance expectation on that water resistive barrier because it can't tolerate cracks and openings because all the air pressure is acting across that. In the 1950s, when we built houses with brick and building paper and no thought about air and water barriers, that wasn't the case. A lot of air pressure occurred across the cladding, some of it across the building paper, some of it across the plastered interior. And so the building paper didn't have to work as well. It's an interesting concept about how our change in wall design has put more focus on the water resistant barrier. So I want to say that it was pretty clear within 10 years of Garden's seminal paper on Rainscreens that it was understood that Rainscreen walls will allow water to cross the cavity and also allow water to drain down the back face of the screen. Well and clearly made. Person by the name of Michael Lacasse, Dr. Lacasse at the National Research Council, did a whole bunch of much more detailed studies in the late 90s that led to the same conclusion that led to the Canadian Building Code requirement of a second line of defense, aka the water resistant barrier. So if I have this detail as a drained wall system, a rain screen, pressure equalization helps reduce the amount of water that passes that cladding, but any water that does pass through, I'm ready for it. I can manage it. And pressure equalization is an enhancement that reduces the amount of water across the cladding, but it doesn't change the need for a water resistant barrier, flashings, and weeples. So that's why the key thing is drainage is required even in perfect pressure equalized walls, which are hard to find. But even if we did perfect, we would still want drainage to be there. And to understand more, we're going to now have to take a segue into the nature of the wind. So this tower here is not a cell phone tower. It is actually a research facility. It's a 200-foot tall tower in the middle of a built-up region in Iowa, which means their buildings are spaced every mile apart. And the flat nature of the terrain means that you get really good wind conditions here. And this is called an atmospheric observatory. It's not just wind speed. They measure all kinds of things as you go up this tower. I'm going to show you some of the results from wind measurements to give you a feeling of what wind looks like. I chose this day, the day of data I'm going to show you, because during that day and this time, the wind conditions were seen as extremely high. Tractor trailers were being knocked over on the nearby interstate, that kind of thing. And yet, the pressures are actually quite a bit lower than we would normally impose on a normal water penetration tests. So just take a look. There's a few things to notice here. I've got actually 3 traces. This is over approximately 5 minutes and 2 seconds. And you'll see that the red line is 66 feet above ground. So what is that? 5 stories up, 6 stories up. The blue line is 16 feet above ground. So that's like 2 stories up. So a couple things. One, as you go higher up, the pressures get larger. That's kind of a given. But more important, I want you to notice is that over this 5-minute period, pressures vary quite significantly. They vary rapidly, and I haven't even included direction here because it's more stable. So let's just focus on this wind pressure over at 66 feet above sea level. We start at 100 pascals, which is about 1/3 of an inch of water column. And then you can see by the time we get to 7 minutes after 7 p.m., we're up to 200 pascals, which is, 3/4 of an inch of water column. And then it drops and rises and drops. The average pressure here is only 138 pascals. That 138 pascals is, by the way, a default value for ASTM E331, which no one uses. Nowadays, we typically use a minimum of 300 pascals. But the 5-minute average doesn't actually capture how much the air pressure varies in time. Here's a couple of the gusts I've looked at here. One of them, it changes 75 pascals in 3 seconds. Another one changes 100 pascals in 6 seconds. Now, while this was a rather windy day, I would call it a windy day. Statistically speaking, they get wind like this several times a year, just so you know the kind of scale of this wind. Okay, so like myself, the wind is not stable. And so we use statistics to measure it. We, average wind speed, usually over an hour. We talk about peak gust loads. That's what structural engineers use to design the cladding attachment systems and the support structures. And we also have something called the root mean squared, meaning how the standard deviation varies. How gusty is it? So all of this data is available. But what matters to our discussion about pressure equalization is that highly bouncing around wind signal is acting at the vents to the air chamber. And now we have to have air flow into and out of the chamber on a second by second basis, not over a multiple seconds or minutes in an ASTM 331 test. No, this has to happen in seconds. And so not a huge amount of air has to move in if you've got a good air barrier, but some air has to move in. And that means that the pressure behind the cladding always lags behind. It sometimes is higher in the chamber than outdoors, and sometimes is lower in the chamber than outdoors. Because the size of the chamber affects how much air has to move in to equalize, big, deep chambers require more airflow, and so they don't respond as quickly. So we normally trade off. If you have a 4-inch chamber, you might want more vent area than if you only have a 1/2-inch air chamber. And this is also why joinery in windows and curtain walls have much less challenges with equalization to these dynamic pressures, because the amount of volume that is served by a vent is much less. So they respond more quickly. But you have usually a few seconds to respond. You can see I showed you some of the gusts, but don't think that we have pure pressure equalization. It's a degree of pressure equalization, or pressure moderation is a term to consider, but we could easily get into the 90% plus equalization, even with rapidly changing pressures that occur in a windstorm. But that's not all there is. What I've shown you here are the charts of the wind at 66 feet. If we think about the wind pressure at 66 plus 8 feet, let's say I have a almost story height wall panel, and I only put vents at the bottom of that story height panel, the chamber is attempting to respond to the pressure signal it sees at the height of the vent opening. But 9 feet up, the pressure is different, not because just wind speed changes with height. That's small. It's because the nature of the trace, I've tried to show the red one is slightly different than the gray one, and there's a difference between those two pressures. That's shown by the green line. And so even if I were to be able to be perfectly equalized, these spatial pressure variations limit how good I can be. So I can have a perfect air barrier and I can have good vent openings, good size, but the nature of the wind is such that because it varies spatially, I can't have a chamber that is served by vents that are too far away. And I'll show you some images here. When we measure pressures on buildings, and some of you may have seen charts like this. This is a simple rectangular building that's obviously much taller than wide. We're looking at the windward face of it. The first drawing is when the wind is dead onto the building. The numbers are a percentage of the wind pressure. I showed you the wind pressures that we measure. Well, 90% of that would be in that sweet spot in the middle. Of course, the air and the wind is flowing around this building. So as it flows around, the pressures on the face of the building drop off. And so these pressure variations can be quite significant. As you can see, going from that sweet spot in the middle to the edge of the building, I can lose 50% of the total pressure. And so when I'm looking at where my vent openings are, the chamber only responds to where the vent opening is. And as soon as I go onto a bit of an angle, I'm showing you 30 degrees here as being a reasonable wind angle, I get really significant gradients of pressure across the facade. And so even though my wall with its vent openings could respond perfect to a static pressure and really quite well to a dynamic pressure, when the wind pressure varies over the face of the building, which it always does, now the assembly can't respond as well. And we can aim for better performance. We will try and break up our air chambers into modest sizes. And that's why the terminology air chamber came into being for pressure equalization as distinct from air gap or drainage gap, because this chamber has a limited spatial extent. I'm using high-tech language here because that way I can charge more money. So the limited spatial extent of the chamber is important to manage how much unequal pressure I get because of the nature of the wind. Nothing to do with what I did with my wall design. So I compartmentalize my wall system to create chambers. Horizontal compartmentalization is commonly provided in practical wall systems today because we'll have flashings and fire stops at floor levels. And so they're natural compartmentalization vertically. Horizontally, plan section, we don't usually have as many good reasons to put in compartments. And so that we have to be a little bit more intentional about. So I want to show you an image here. If I look on the left-hand side, the elevation view, you see the gradients. There are some pretty significant gradients around a corner. Upper left, I'm showing a plan view. Windward face is at the top, side walls on the left. That pressure distribution, which is quite normal, could result in air dragging in through openings, including weep holes, and dragging around the corner and sucking air out of the weep hole around the corner. So this is a very common pressure condition, and it is relatively easy to block a cavity at corners by some means. Sometimes I've seen it done even with backer rods. If you have a 2-inch backer rod and you shove it in the corner, I've seen that for brick walls. We've also seen sheet metal being used. It doesn't have to be perfectly airtight. It just has to be a lot more tight than the vent openings that bring air into the air chamber. So this is an example of how these distinctions are brought into an ACM panel. This is from the Metal Construction Association. They have a technical bulletin. And the image on the left is what they are describing as a drained and back ventilated rain screen. Basically, it's a rain screen that they're not compartmentalizing. To them, the distinction between a pressure equalized system shown on the right and a drained and back ventilated rain screen on the left is that the rain screen on the right is compartmentalized, and that they are saying makes it pressure equalized. And it certainly will improve pressure equalization performance under real world conditions. I'll point out, however, that both of these systems will perform exactly the same in a laboratory test, because a laboratory test does not include spatial variations. And so you will see no difference in performance between these two systems, whether they're compartmentalized or not. So just that's why it's so important to understand what's actually happening so that you don't get too carried away with what the tests tell you and how you design. What size should the compartments be? Heck, I don't know. That's sort of the answer that science has come up with The best research that I know of is dates from 1996. This was their draft recommendation at the time. These were based on some pretty serious wind tunnel tests. Um, and they're limiting these sizes based on a goal of 75% equalization. So not 90%, just 75%. And when they were describing it, it was based on a fraction of the width of the building. So the horizontal size was, if you near the tops and edges of the buildings, the compartment should be no bigger than 1 meter. Actually, near the middle of the building, the compartment should be no larger than 1 meter, which in a way makes it kind of impractical. So these numbers came out of their analysis, and there's lots more research that could be done. But realistically, these are saying the 1 meter is what you should be choosing. And that's pretty darn small. So when we measure in the field, and I'm getting near the end here, so there are not a lot of field measurements. I could do an hour on field measurements of pressure equalization. There's not a lot of field measurements. This is one of the best ones. Again, Natural Research Council of Canada. This was on a high-rise building in downtown Montreal, 30 stories or so high. And the panels that made up the wall were designed as precast concrete, pressure equalized, exceptional air tightness, all well-designed vent openings. And the red line here are actual measurements of the pressure across the cladding during a relatively windy period. Now, it's definitely a taller building, but these are significant air pressures. And you can see that it's probably only about 50% pressure equalized, and yet it followed all of the best practice rules of the time. So this just opened people's eyes as to how important spatial variations were and how difficult it was to get perfect equalization. So this is another way of presenting the results, meaning they just looked at the number of seconds when there was the pressure difference across the cladding was 40 or 50% of the total pressure. And as you can see, almost half the time, it was 40 to 50% of the total pressure was across the cladding in a pretty well-designed system. So following on from some of that, there were a lot of tests done in labs where we did things like dynamic sine wave tests. And this is similar, and I think it helped develop test standards like AMA 508. And they did them in the lab. And then we were also, several people were able to, say, this is simple to predict with a computer model. And the top line on this chart says the circles are physical measurements. They actually they put sine waves on in a lab, and they measured how well equalized things were. As long as the gusts were less than about 1 second in duration, we were in the 90s. It was great. However, in the field, the pressure equalization performance shows the jagged line that is significantly less. And by the time we got to gusts that were only 1 or 2 seconds long, we were under 50% equalization. And that was based on the physical measurements, all about the spatial characteristics of the wind, because it should have performed as per the solid line, except the solid line was all uniform pressures, some of them dynamic, but that wasn't the hard part. It was spatial that really hurt us. So the takeaway here is the nature of wind pressures will often limit more than system design. If you follow good practice, you will have good pressure equalization performance in the lab, and the limit in real life is the nature of the wind pressure that's acting on.
John, a couple questions here before you jump onto this next section. Is there any way that we'll get to a point where we can maybe recreate the real world conditions in laboratory conditions specifically? Are we heading down a path to get closer to that? Because it seems like maybe we're okay.
It's already been done. They have all you need is lots of money.
Fair enough.
They have developed really sophisticated actuators where you can put an individual actuator over each vent opening and run it through a realistic pressure signal measured from the field, and that will work. And it has been shown in university level research. But the problem is that you're going to have to spend $50,000 on a test, and it doesn't actually tell you that much, other than you should spread the vents out across the facade, make it uniform. You should
Yeah.
use compartment separators, and despite all of that, you're going to use a water resistive barrier with flashings and weep holes. And if you do all of that, what do you need to test for?
So
So
kind of one more question on that. There's a handful of questions that kind of tie back to that previous slide. When it comes to, system design maybe not being as impactful as the pressure, right? As the wind pressure and how it limits performance. How might we consider material selection or system design when it comes to things like the thickness of the cladding that's being used, things that are maybe going to inhibit some airflow, like a bug screen, additional insulation in the cavity? How are those items going to impact the potential performance of a pressure equalization?
So in a way, I would. This is not a bad time to talk about it, but in a way, that's sort of the ending conversation we should be having.
Okay.
So the one place where I've given you a number was in the vent area, and so 0.1% of area of the wall panel as vent openings. Now, if you block those openings with insect screens, well, obviously you need to increase the area until the airflow is equal to 0.1% of unobstructed flow. So how would you do that? Well, it's not as expensive a test, but you would blow air through whatever you're using, and you would say, this restricts airflow by 50%. I need to double my vent area, as an example. With respect to the volume of the chamber, slightly harder to answer, but not much. The computer models we have are actually quite accurate at spatially uniform pressures. And so we would look at, okay, what happens if I have a 4-inch cavity with 3 inches of stone wool in it? Versus 1 inch. Well, it turns out it's not that huge of a deal. And normally the answer is, just add some more vents. And that really solves most of those kinds of questions. The thing that isn't well answered is how much should I compartmentalize and where should I put my vent openings? And that really is, you do want to distribute your vents across your compartment. It was originally deemed that, I should just put the vent at the bottom. But actually, some of that wind tunnel work and so on is showing that, you're better off having vents left, right, top, bottom, so that it's spatially, the air chamber sees a spatial average of air pressures. But compartmentalization, unanswered question. Certainly corners, certainly ideally near parapets, but there's not a good answer to that. And I've mentioned some of this stuff already, Andrew, but again, I just want to reinforce that most of the current standards are spatially uniform pressures. And, almost every window out there is tested under spatially uniform pressures. And it doesn't actually capture any of the pressure equalization performance really at all, other than that air tightness thing. But there are dynamic test standards. In Europe, they have the EN 12865, and it's not really a dynamic test. I mean, it takes you pressure, it rises to a high pressure, holds it for a few seconds, falls. So it captures a little bit of it, but not a lot of it. Like a 15-second cycle time is pretty easy for almost everything to meet. The ASTM 2268 actually specifies a 2-second cycle time. That's challenging, and that means that you are asking a fair bit of it. I believe, I wasn't involved, that is why the AMA 508 test standard used a 3-second time, because 3 seconds is already pretty challenging. Now, that gives us a dynamic response as well, but it doesn't give us a spatially varying response. And to your previous question. So we try and impose, something like a triangle or sine wave. Oftentimes the pressure only drops down to some small positive number. We don't let it go to zero so that it's always blowing in, because in real life, that's how it works. The pressure in the chamber will closely follow with some delay and some small reduction in peak. But in most cases, as long as you have a reasonable amount of vent area, like I've said, you'll end up with good pressure equalization in this test. And that means, you'll often get pressure equalization in the field, but you should accept that a lot of time you'll only get 50%. And that means you should be aware of that. So, and this is that just the key takeaway here is that all standardized tests do not account for the spatial variation of the wind, and that can dominate large panels. Large meaning, 4 or 8 feet in size. It's another reason why joints do far better, because they tend to be spatially more restrictive. So I want to answer that question about the cladding thickness in a moment. But so my recommendation, and I will grant that this could easily be, argued about. I recommend focusing on effective water resistive barriers, drainage, venting, and air barriers as that's your baseline. That's what you've got to do. Pressure equalization usually does, add some performance to Rainscreen walls. In many types of systems, it adds very little performance. Those systems I'm talking about, systems that have lots of openings in them anyway, such as brick veneers. They leak like crazy, whether or not they're pressure equalized. Metal panels properly have the most benefit because they don't leak at all, except at those joints and cracks. So they can have some significant benefits from pressure equalization. Ensure large vent areas, I'm adding as a special point here because frankly, that's probably the one thing you can easily do that will enhance performance without getting lost in the weeds about exactly how big, how much, and how it's going to depend. With respect to the question about cladding, I started this seminar quite deliberately saying the focus was on managing rainwater penetration. But there's no doubt that there are people who are interested in saying, hey, if the pressure across the cladding is less, doesn't that mean that I can make my cladding attachments lighter? Doesn't it mean that I can use thinner metal with less bracing and not get wind buckling and so on? Okay, there's a big difference between rain penetration concerns and these types of structural concerns. Because under structural load conditions, we're looking at some of the worst gusts in any given year or over the lifespan of the building, frankly. You're designing for the worst 1 to 3 second long gust that occurs once every 20 to 50 years. Under those types of pretty extreme conditions, the pressure equalization performance is likely to be significantly worse than what I'm talking about here. And in fact, it has been found in practice that when loads on claddings have been reduced by regulation, as they were for vinyl siding, is that vinyl siding began to blow off buildings. And we know this is a large-scale problem from an insurance industry, and they did a bunch of research, and they no longer allow you to use reductions in the attachments and the thickness of vinyl siding due to pressure equalization, because the field experience and research showed it wasn't sufficiently reliable to make meaningful reductions. That doesn't mean it applies to all claddings, but I have been involved myself in 3 separate large buildings where the cladding was explicitly designed to use less stiffness and strength because of pressure equalization. And the reason I was involved in those buildings is that all of them had the cladding blow off. None of them at particularly bad wind conditions, kind of worst of the year. One of them within 4 months of construction, and the others within a year or 2, panels were blowing off. So I think my very limited experience, but the broader experience of the industry and what we know about science, It is technically possible to reduce the thickness of the cladding, but there is very little confidence given our past track record that we'll get it right. So I think you should be quite careful about it and make a real trade-off about whether you can reliably predict these spatial pressure gusts. Sorry, long question. So I'm going to leave it there and we'll get right into the questions and so on. Although we've already been a bit of that.
Yeah, there's still definitely some terrific questions rolling in here, so we'll jump into a few of them. One question was about lost on me. Let me find it again here.
Yeah, there's lots of questions.
Yeah, so when it comes to like the rigidity of the substrate that's supporting the air barrier, how much is that going to influence the response of the equalization in that chamber? Is there anything that we can kind of design that substrate to impact in any way, or is it really not going to impact as much as the other
Let me understand
geometry of the cavity?
the substrate. What do you mean by substrate?
So what we're attaching the air barrier to. So whatever's going on behind that air barrier, is there any influence of that material to how fast that chamber can equalize?
You just want it to be rigid. But so yeah, rigid is, I guess, the thing you're looking for. And that way it doesn't change volume with pressure. Usually easily done, but if you use sheet metal instead of gypsum sheeting, that becomes a very practical concern. In curtain wall spandrel panels, it actually can be dominant. So spandrel panels and curtain walls, if we want to, I don't know whether that's Rainscreen cladding or not, they have a problem achieving good pressure equalization performance based on physical measurements and even lab measurements because they have quite small vent openings, they have quite large volumes, and they have very flexible back pans. That combination all fights against good pressure equalization. So that's just an example that you might apply to a wall if you'd like.
So speaking of that kind of concept of things that might fight against pressure equalization, there are some, design approaches that really focus on the stack effect, right? We want to kind of have that hot air moving continuously through long swaths of sort of chimney in a rain screen system. So how does that approach versus the compartmentalization in a pressure equalized system, how do they work either against each other or maybe for each other in some ways?
Okay. Actually, we have good information, I believe, on this. First of all, the amount of airflow that's going through behind the cladding in either a ventilated cladding or a pressure equalized cladding is so small, it does very little for removing heat. Stack effect is driving airflow, but the amount of airflow is so small, it does essentially nothing for heat. So don't think that you're getting a benefit of cooling the building by putting vent openings at the bottom of a 2-inch cavity. Utter rubbish, physically measured, and also calculations would show not going to happen. But I would say more importantly, we tend to have these horizontal separators that separate the space vertically because of other requirements like accommodating movement and not cracking the cladding, like making sure that we have fire stops between floors. And that will always and properly dominate the very small benefit I might get by having a taller building to drive slightly more airflow. It's really dubious.
When we get into dubious questions that we're rocking here. Let's see, what else do we have?
So I think I saw one question here, which I get commonly. Is it a problem to put vents at the top and bottom, which encourage ventilation? And does that degrade pressure equalization performance? And the short answer is likely not. And it goes back to the spatial pressure variations. By putting vent openings at the top and the bottom, yes, you get stack effect ventilation, which helps with drying, but you also get averaging of the pressure in the chamber with the exterior air pressure variations. And so it does harm the pressure equalization point for performance at any given vent because, of course, it's not responding only to that vent now. But on an average of that whole panel, whether it be 4 by 4 feet or 8 by 20, on an average of that panel, the performance is better. And that's based on somewhat limited research, but that is what the research does show. There's really no research that shows that vents only at the bottom result in better performance for pressure equalization. There's only research to say that vents top and bottom appear to work better.
I have a question here, more of a comment perhaps, but it states that nobody really wants to install cavity bathrooms. So nobody nobody really wants to compartmentalize. Do you think
Correct.
that we'll ever really get to a point where PE walls are performing the way that we intend, or they're maybe more commonplace in design and application?
I think actually we have PE in practice a lot more than we think we do. And but again, it's all a percentage of PE, right?
Sure.
There's lots of people who think they're getting 90 or 100% and they're actually getting 50. And there's lots of walls where people don't even think about PE and they're getting 50. And I mention that because there are compartment separators in a lot of our buildings by nature of us putting a balcony in, by putting in a window or an air conditioning sleeve, or using small cavities. They actually there's a concept by the friction of airflow in a cavity, if it's small, acts like a smeared out compartment separator, because friction over several feet act as a compartment separator. And those are real things. And that's why I focus so much on the corners, because that's where we know we have a large pressure difference and we could do something. But I actually, yeah, I don't think we're going to get to the nirvana where we're getting 90% pressure equalization everywhere. And I don't think it's needed. I don't think there's a benefit to us. But I do believe there's a benefit in trying to get better vent area and better pressure equalization, manage some of these compartments. Um, and yeah, I agree. It's rare to see people block off those corners. I agree. But it's easy to see architects change claddings all the time. So every time they change claddings, which they do randomly around the building, there is an opportunity and a reality usually of a compartment separator.
Yeah, I think it kind of ties back to the conversations we had about achieving some sort of moderation, right? Pressure moderation across the building versus true equalization as an approach. Um, So you mentioned kind of different materials. So for the manufacturers out there on the call, there's a question about, is AMA 508 really the best test method for them to prove that they are, kind of providing a PE system, or are there other approaches you might suggest?
I don't think 508 does anything about showing that you have a pressure equalized system. It does nothing. It does show that you have a dynamic, spatially uniform response. That's good, and that's good. But it's more the idea, as I showed the Metal Constructors Association tech guide, being able to explicitly identify how you are doing compartmentalization. It's not a test, guys. It's like, tell me how you're doing it. It doesn't have to be expensive and go. You could just give us a drawing and say, all corners have this block. Every so many meters or feet, I have this block. That's a bigger step towards ensuring pressure equalization. Once you've got the vent area right, which 508 shows you, that I don't think that the 508, though, raises that issue at all. And it's a very important one.
So I got some questions rolling in here. One question I thought was interesting, when it comes to like a stucco application, potentially with, some sort of cavity behind, have you seen a stucco application achieve kind of a pressure equalized application?
I haven't done it with stucco, although people do try.
Mhm.
I can't say if they're successful or not. I have, however, measured physically an EIFS system.
Okay.
So in the early days where they were draining it, they were saying, hey, why don't we actually measure the pressure equalization of a 1/8 inch drainage cavity, which was formed by adhesive strips. And that actually performed reasonably well. It was actually quite good. It was partly limited by the fact that it only had vents at the bottom, but it still had pretty good performance. I don't see any reason stucco couldn't use this, but remember, stucco is primarily leaking at cracks and openings. And once you have a backer board to put it over furring strips to create a cavity, it's primarily leaking at all of the details. Every one of those termination metal pieces leak like crazy. And they don't leak because of air pressure, they leak because of gravity and surface tension. And so, if I'm doing those types of systems, my focus is on those and a good WRB, flashings, etc.
So we have a couple of folks have commented on a CMHC document, the Rainscreen system, that provides some guidelines on compartmentalization, some good details. Is that something you're familiar with? Any comments on that, just generally speaking?
Yeah. So first of all, that document I showed was the base research sponsored by CMHC for compartmentalization. However, their best practice guide series was done in around the 90s, exactly when I was starting my research on this topic in earnest. And there was those documents have to be remembered in that historical context. There was a little bit of an obsession about pressure equalization at that point, and not enough of a recognition of drainage and flashings. And so, but the details generally are good performing details. I just think they do need a little bit of modern polish and look at it through the eyes of what we know now today. It wasn't all better in the old days, despite what mom says.
uh, all right, let's see what else we got here. We got some folks logging off, but
Well, I hope so. You'd think they'd get bored eventually, right?
enough looking at my face, I think. I think we've addressed just about everything here.
One of the questions was about a Rainscreen mesh product, and that's part of the challenge with calling it Rainscreen, is that there are entangled meshes and dimpled sheets and so on that create the cap. Can they be used in pressure equalization? The short answer is yes, but the longer answer is we really don't know a lot about how those types of products act to dynamically resist airflow in and out of the cavity. We actually only know a little bit about how they statically affect, so only a few measurements of airflow. But there's also a worthwhile question to ask. So do these entangled mesh and dimple sheet products dynamically resist airflow? It's quite possible that it's not a meaningful resistance and they would be good. But it's also something you'd probably want to accommodate and accept that some of it won't be so good.
Is there any like test method or anything in place or anything that can be used to kind of navigate that, or
Yes,
is it
there is
mostly
an
calculations?
ASTM standard that is based on some work we did at Waterloo many years ago, and I think it even has Rainscreen membranes or Rainscreen meshes or something in the name. I forget the title, but there is an ASTM standard for measuring airflow statically through these, and I would just say this hasn't been adopted for dynamic. Okay, there's a question here about someone doing their PhD. You see my email, please. You know, that's the kind of question. You should send me an email. I'm glad to help you out. More than glad to help that out. Yeah, Andrew, I think we've got a lot of these, although there are a lot of questions. But no, I think we're doing okay.
Yeah, a lot of we've kind of compiled a few of them into single questions because there's a lot of folks,
Yes,
having the same
similar questions.
consideration.
Yeah. Makes
Yeah.
some sense. Yeah. So I guess we should say that they should pay attention to RAINA's website because there are ongoing opportunities. I mean, they just finished their annual conference, which is always worthwhile. This year it was together with the Air Barrier Association, which you can see why those two would want to talk to each other. So it's not just these types of webinars. There's lots of opportunities to carry the conversation on and keep everyone up to speed and on their toes.
Yeah, absolutely. And of course, these will be on there as well. So for any refreshers, I think John and I, this is maybe second or third one we've done in this series. You get to see our faces smiling and talking through some of these earlier topics as well, which I think is a great foundation was set for some of these more advanced topics as well. Yeah, I don't know if there's anything else we want to throw out there.
Well,
Yeah,
if not, I guess we'll say sayonara or auf Wiedersehen.
they both apply. All right,
And
thank y'all.
I'll see you soon. Okay.
All right, take care, y'all.
Bye.